Jan Igelbrink is going to give us the next talk. Did I pronounce your last name correct?
Actually, you pronounced it really right.
Okay, good. Go ahead.
So
you can pull this off and hold
I
it in your, yeah, sure.
Perfect. So I'm talking about ancestral reproductive bias in branching trees under various sampling themes. And it's all joint work with my co-author Jasper Ischelbeck, who's a PhD student in Frankfurt. And this is a frightening title, I must say, even for me. So I have no idea of biology, and ancestral reproductive bias sounds very like it's coming from biology. But I have some idea, I think, about basic probability theory. And I want to teach you only basic probability concepts and advertise even state-of-the-art mathematics can still be understood with elementary facts. So imagine for some time you're in this forest. That's actually the rainforest in Rwanda. Remember the conference that will happen in Rwanda? Imagine you're in the forest. I give you a simple task. Select a random tree. Okay, one of you guys might say, okay, I go through the whole forest, I give numbers to all the trees. Yeah? Tree number 1, tree number 2, tree number 4. Let's say we have 1,500 trees. I just select a completely uniform number between 1 and 1,500, and that's the tree I've chosen. Okay, that's the way a human being would do it, but let's assume you're a bird, you are flying over the forest. You see the leaves of the trees, right? And isn't it natural to say, let's just pick a random leaf. Just pick the leaf of your random choice, and then select the tree that corresponds to this leaf. Is this the same output, at least in distribution? Actually, it's not. And that's a central message from a bias. That's really the elementary bias. You select a large tree. When you randomly select a leaf, you tend to select a very large tree. Yeah? It's obvious because large trees have more leaves. So in distribution, you will select a different kind of trees. And there are many such biases in biology. And biologists, they always start taking cell samples and so on. They analyze mutation rates. And then they see, oh, the number of mutations does not match my expectation. Usually the answer is a bias. And I want to tell you a story about 3 very nice biases, and at least one motivated by biology. And I think this picture is slightly corrupted, but no matter what. The title of this nice paper by David Cheek and Samuel Johnston that appeared last year is Ancestral Reproductive Bias in Branching Processes. And when you paid close attention, this title sounds very similar than the title we have chosen. So David Cheek and Samuel Johnston actually motivated us to write this very, very short paper. So let's give their abstract a look. They write, consider a branching process whose reproduction law is homogeneous. Wonderful. So you have individuals. After some time, they maybe get children, and individuals always die when they get children in our world, or they don't get any children. Yeah, it's completely time homogeneous. They don't care if it's the year 2000 or 2020. And what they say is, okay, let's look at some time t. If there's any individual living, let's select one uniformly. They think of selecting cells because they are motivated by biologists. And then they write, looking along the sampled cell's ancestral lineage, we find that the reproduction law is heterogeneous. So I've just told you, your reproduction law does not depend if it's the year 2020 or 21 or whatever. But when you look at your ancestral lineage, just in time back, of one uniformly sampled individual, there's a heterogeneous reproduction rate. Something is odd. And yeah, let's try to find an explanation throughout this talk why this can be the case and why there's no error. I mean, imagine you're a biologist, you see that. You say, okay, I follow this ancestral line back and I say, mutations happen at reproduction events. And then there are so many mutations that you're really surprised and you think, okay, the data is wrong, the experiment is wrong, I have to start over all over again. No, you haven't. There's an explanation. Okay, second model. No worries, I will repeat the models very often. A second bias. Jochen Geiger, also a Frankfurt guy, and also maybe the reason why we studied this, because we know his work very well, he did the following. Most of you will know Golden-Watson processes, right? Just this process I described. An individual, after some exponential time, it will either split into 2, 3, or it will just die out, and all its children do this independently. And of these trees, there are many, many, many complex limit theorems. And Jochen Geiger was a very smart guy, and he had the following idea. We proved these limit theorems by drawing these trees, essentially. I mean, what's there to do when you have a random tree? Draw it into the plane, embed it into the plane, and as soon as you do that, there's a most left line that lives till time t. It's just in the picture. You just look, what's the most left line in my picture that lives till time t? And Jochen Geiger used this construction, essentially, to build up the whole tree. However, when you look at the most left line, that's a very special line, right? You will observe another bias. Okay, and one last model, growing conditioned trees. That's a title only Anton Kolbinger can proudly say and write down, such a picturesque title. We really grow conditioned trees. Okay, we are mathematicians, we are not growing trees in the garden. In some sense we are. And what is he essentially doing? What is this model doing? They say, let's consider something like maybe branching Brownian motion. That's just a particle that walks through space randomly. Up after some time it splits into 2 and its 2 children walk randomly. And they analyze the following. We condition on the event that at time t there is one particle at a specific point in space. We condition on that. So there is one. So this particle has an ancestral lineage. And we can observe where do they come from, what reproduction events do we see along this lineage. And what you will see is no bias anymore, which is kind of surprising after the other stuff I told you, right? Selecting a uniform individual, bias. Selecting in some embedding of this tree, of your ancestry, the most left, okay, another bias. There, no bias. Okay, 3 trees. Uniform selection, most left one, and growing conditioned trees. Let's start with the first one, and I will not bother you too much with details, but with another abstract. So Jasper and me, we wrote in our abstract, our proof sheds light onto the probabilistic structure of the rate of reproduction events. Remember, the rate Cheek and Johnston observe in the first model is time heterogeneous. And then we write, we also look at the, we use the same method for this stuff by Geiger and for the third model. Wonderful. So I'm standing here and telling you, we shed light onto this thing. Let's see if I can really do that. Okay. Let's get to the fact, what are these branching processes in a picture? I've described them, but we should see a picture. So we have one individual, namely this. After some random time, it just splits into a random number of individuals. In this picture, those are 3. And its children do the same. This children just dies, splitting into 0. This children just die, splitting into 0. This one splits after some time into 2. Okay. So we have some kind of continuous branching process, and now I will need some notation, sadly. Okay, 3 letters. The first is the capital N. Capital NT is just the number of individuals at time t. pk is just the probability that you have k offspring when you die, and your lifetime, the time after you get offspring, is just some distribution. Choose your favorite one. Many of you will like the exponential distribution. Okay, so we are in this first tree. How do we model that in an elementary way? I want to describe this uniform selection very, very easily. So what I will do is, on the event that there is actually an individual at time tm, the tree could die out, I will just assign all those individuals a random number between 0 and 1. Imagine you all being those individuals alive at time capital T. I assign all of you a random number between 0 and 1. And now, I select the one of you who has the largest number. So let's say Jan had 0.1, Nutzer had 0.3, Abdu had 0.9. Okay, largest number is Abdu by randomness, and actually this corresponds to just randomly selecting one. Yeah, just having a die with 3 faces. Okay, there is none here in the room, and tossing. And let's call this individual with the largest name, number, V, and S be its mark. And J, capital J, when we look back, its ancestral lineage will be the number of reproduction events we see at times T1 till Tj, and they have sizes L1 till Lj. Okay, even more notation, let's make a picture, right? We have this very nice tree, slightly different. We have all those individuals alive at capital T. We give all of them their random marks, 0.1, 0.28, oh, here's one, 0.967, obviously the largest one. So this individual is now V. And let's look at its ancestral lineage, right? Like I just said, that's this one. So what do we observe? Okay, at time T2, at the second reproduction event, this individual, it has split into 2. So L2 by definition is 2. At this time, this individual has split into 3. So L1 is equal to 3. So we have observed 2 reproduction events, J is equal to 2, at times T1, T2 of sizes 3 and 2. And now, okay, that's an example, but you know, I'm a probabilist. I do probability theory. I want to know what's the probability that I actually see such an ancestral lineage. Exactly this one, for example. Or what's the rate when I just look at which these reproduction events appear when I look into the past? And this is described by this frightening looking theorem. At least for me, it's still a little bit frightening, even if I proved it. Or I think I did. Okay, so the probability that you have an individual at time t, yeah, otherwise there's no tree, that you see j reproduction events at those times of sizes L1 to Lj, that the largest marker is S. Okay, it's essentially a probability that you just have lifetimes of the corresponding length, wonderful, times a product. Okay, the probability that you see events of this size times the number of offspring makes sense, right? When you have L1 many offspring, either one of those children could generate this largest mark at the end. Yeah, some exchangeability idea. But then here's this strange thing. It's the expectation of S to the power of, the size of a tree with rest living time T minus Ti to the power of Li minus 1. Anyone has any explanation for this thing? Yeah, that's exactly how I looked when I saw this result in the Cheek and Johnston paper. I had no clue. So we can make it a little bit easier by just looking at the time discrete process, yeah? You just die after time 1 and you get your offspring or you don't get it. Then it still looks frightening, you just don't have this term anymore because it's 1. And you can then even answer the question, at what rate do those reproduction events appear? Right? That's a very fancy way of saying there's some time in a Gemius Poisson point process and so on. But essentially, you look back, what's the expected time you have to wait to see a certain reproduction event, certain size, and so on. Okay, it's like somehow when we choose exponentially distributed lifetimes, lambda times L times PL, okay, wonderful, time homogeneous stuff, times some, again, extremely frightening term. And for this I need my coauthor because I always do computations wrong when I do something like that. But the important part is capital T minus small t. There's a small t. This rate is time inhomogeneous. Yeah, like I said, we start with a time homogeneous process. We look backwards, and it becomes time inhomogeneous. So actually, when we were both frightened by this result, we were sitting in the Austrian Alps, where we have our yearly seminar, exactly at the space where we've taken this photo, and we're thinking about it. Cheek and Johnston, they proved this miraculous thing, but we were not really understanding their proof. I mean, it's a great proof, it's a great method, but was too hard for me at this point in time to understand, and we were thinking, how can we prove it in another way? And okay, let's try to prove it, right? We have a theorem, we know it's true, it's already proved. Let's try another proof. First of all, what's the probability that you don't even see any reproduction event? Okay, that means the individual you selected is just the same individual you started with, and there was no reproduction event at all. So it's just the probability that this individual lives exactly at least time t long, okay? Both sides are equal by definition. But how do we continue from here? I mean, okay, we look at this event that the first reproduction event happens at some time and is of size L1. Okay, now all those L1 children behave the same, completely exchangeable, right? At all of those, we start a new tree in essence. Yeah, and after some time, one of these ones needs to split into L2 ones because we selected an ancestral lineage where we observed exactly that. So this happened at some point. And again, those trees are all the same by exchangeability and distribution. So let's go to a slightly less complicated expression. What's the probability that we see at least one reproduction event that happened at T1, which is of size L1, and the marker S, yeah, which is in a small interval around small s. And I tell you the following. Remember this picture I've shown you before. After the splitting into L1 many individuals, you just have L1 many completely exchangeable new trees. So all of those trees get marks at the end, right? Because all of them have potentially individuals at time t. So let's just do the following. All those trees, they live for a time t minus t1. They are in distribution as large as n t minus t1. So let's take independent copies n1 till L1 of this random variable. Okay, this gives us some L1. This gives us L1 many random numbers, right? Integer numbers. And we just take tilde n1 many uniform ones, tilde n2 many uniform ones, tilde n L1 many uniform ones, okay? So we have trees of sizes tilde n1 till tilde n L1, and to all individuals of those trees that are alive at time t, we assign again those uniform names. Yeah, I've just broken down the whole tree to the families we see after the first reproduction event. Nothing happened so far. That's the same setting. And what I do is just I say, okay, Sk is just the maximum over those markers in the case family. And S superscript L is the maximum over the maxima of those families. And then, of course, like the probability that we see this event, it's just a probability that after time t1 there is a reproduction event of this size, times, okay, one of these families needs to live till time t, and there needs to be a marker, namely the largest marker, in the event S. So we are left with studying this object. But now you won't see it directly, but take 10 minutes time and you will see, oh, I learned this in elementary probability, probability 101. That's just maxima over a random number of uniform random variables. So what I called an elementary fact at the beginning is, what's actually this probability I've written down there? How do we compute it? And the elementary fact, let's call it a lemma now, a little bit more serious. Okay, it's L times, oh, there's this generating function we observed, times the probability that a family lives as long as that, yeah, namely that there's an individual alive, and the largest mark of this family is in the S. So why is this the case? It's exchangeability that works here, okay? By exchangeability, that's just L times the probability that one family lives that long and that all the other maxima in all the other families are smaller than S, yeah? It could be every family. They are all exchangeable. So the probability that one is the same for all of them. Exchangeability just says it's L times the probability that exactly one is it, and all the other maximas you see are smaller. Okay, but now, like I told you, all these families, they are exchangeable. They have the same distribution. So what's the probability that all the others are smaller? It's the probability that one is smaller to the L minus 1. Okay, there are L minus 1 other families. And the probability that the uniform one is smaller than S. You know, that's the generating function, right? And then we spit out a generating function. So what have we actually learned when we now plug this in? Wonderful, plug this in for this probability. Then this frightening thing becomes exactly the term we have seen in the theorem before. So, okay, back to the question, what is this meaning? Essentially, this means a uniform selection, since it corresponds to selecting the largest mark. It gives you a bias because the ancestral line you will have selected, most probable, it will be a line where there are a few more offspring events because of the fact that there is competition around the maximum mark, which is not obvious at the beginning when I say selecting uniformly that it has to do something with maxima, but it has. Okay, so to not go over time, I will now tell you a very brief story about the other two sampling schemes. Let's start with Jochen Geiger's, right? It's the more beautiful tree here. So the leftmost ancestral line, how do we do that? We do it in a natural way. When you get children, you give your children a name, right? I'm a mathematician, so my children will get numbers as names, at least those here. Okay, so every time there's a birth event, I just assign a name uniformly on 0, 1. And when I give you your name, the name of your father, the name of your grandfather, you can trace back your complete ancestral line this way. Yeah? And we is just the individual whose marker along the entire ancestral line comes first in the lexicographic ordering. Sounds terrible. Here's a picture. So we have the same tree. We give names to all the individuals. Yeah? And now we just order the tree. So we will have this one left, this one in the middle, this one on the right. The same we do here. We change the 0.2 to the right. We flip this. This is already in the right order, and this will flip. Looks like that now. It's the same tree, different embedding. And now, who's the one who's most left in the lexicographic ordering? Oh, the one who's most left in this embedding, right? Oops, this line. And that's the line we would now observe. Okay? So what do we ask for a question here in this model? Nearly the same question. How many reproduction events? When do they happen? But additionally, we ask something else. How many lines were actually left of your line in this embedding that die out before time t? Here we call this the ki. Again, let's do an example here. Okay, this reproduction event, there were 3, so L1 is 3. There was no line left of you, so K1 is 0. Here there were 2, but the line left of you died, so K2 is 1. Okay, here there were again 2, L3 is 2, but you were again the most left line, K3 is 0. And again, you get a theorem. What's the probability to observe such an ancestry? But forget what you see, like forget all but this here. This here is, okay, probability to see an event of size Li times generating function. And most notably, that's different, right? It's like probability Tn minus Ti equal to 0 to Ki. That's much different from the generating function we have seen before. But still, it's a bias. It's a different bias. And if you would now be really, really into it and want to dive in these elementary facts, there's the next elementary fact. But don't mind now. It's essentially you play the same game and translate it again in random numbers and random families, and how many are smaller than you but don't overlive, right? It's the same strategy. Okay, so I'm now quite bold and I'm crying loud. Oh, we have a quite cool method. Yeah. What about the last model in the last minute? Last model, okay. We have a branching process, branching Brownian motion, going through time, splitting, and we condition on one particle being at a specific point in space at a specific time. And yeah, we just need 2 technical conditions. The first one is all marginal distributions are identical. Okay, wonderful. Think of branching Brownian motion, yes? The particles all behave the same. The second one is almost surely no pair of markers is equal. What do I mean with this? Think of the fish in the ocean. Yeah, even if a fish gets birth to another one, then those two fish swim independently through the ocean. But there will never be two fish at the same point in the ocean, right? Two fish cannot intersect. Maybe when you look from above, but in a three-dimensional world, two fish don't intersect. Yeah? No two fish at the same point in the ocean. Okay, so we condition on someone being at this time t at this point s. And we trace back its ancestral line and ask, when do the reproduction events happen, of which size are they, how probable it is to observe something like that. And then there's another theorem, and essentially it tells you condition on there actually being an individual, yeah? And then all you see is, okay, the same story as before. The expectation of NT here in the denominator comes from the conditioning, forget it. That is the important part, Li minus PLI. And that's just where we started. That's the growth bias coming from selecting leaves out of trees. You tend to select a larger tree. And that's the general bias, which we call no bias in this case. And yeah, guess what the method is to prove it? I can tell you it's even easier than the other two, because there's only one thing you have to remember. No two fish are at the same point in the ocean at the same time. There is no competition at all. When I tell you, you made it in the next 10 years to this point in the ocean, then I can tell you no other fish, no matter how many reproduction events along any ancestral lines there are, will make it at the same point. There are no two fish at the same point in the ocean. Okay. Yeah, let me finish with advertising some literature. This paper of Cheek and Johnston, and even if it maybe sounded like I criticized it a little bit, I want to emphasize it's an incredible nice paper, and that's the point how research works. You start with a theorem, someone proves it, and then you start thinking about, can we prove that in a more nice way, more elementary? And that's also the way the work by Jochen Geiger is written, and in case you need someone writing a bachelor thesis, that's a wonderful topic, I think, with not enough bachelor theses written around it. Yeah, and because I'm also connected to this project, let me again advertise this conference. Yeah, and maybe regarding the question who's eligible to go there, as long as it makes sense for you to go there, as long as it makes any reasonable sense, I think there's most of the time a solution, but it should make sense. Yeah, thanks a lot.
Thank you very much, Jan. We should start charging you for the advertisement, okay? Okay. All right. Any questions? Very interesting talk. Mm-hmm.
Thanks, Jan Lukas. So, is there possibly an interesting problem there in terms of like reconstruction? So, for example, like let's say I'm an individual and I have like a very long, lineage, very long genealogic tree, and like I know these numbers, these L1s, like over my past for a long time, and then I ask, so can I recover this original probability distribution from this data? Like, is it easy? Is it hard?
So at least you can try to recover the expectation of it with what we obtained. But actually you are right. Because you have this, let's go to the first one because it makes the most biological sense. That's the theorem. So, okay, you have like the waiting time distribution. Normally biologists just assume exponential. So you can say I can always recover this term. Then you have those, and I think that's the interesting part because the distribution of the NT, it only depends on the waiting time and on the pKs. So you now only have an equation on the pKs and the N, and when you have enough observations, this could spit out actually enough to get the pKs out of it again. Because you know, okay, when I have seen them with this rate, the pKs must have been that, but I'm not sure if this equation has a unique solution. I guess it has because of these generating functions stuff and uniqueness, but I'm not sure.
Thank you. Any other questions? Okay, and maybe I have one. So what is a possible extension of this work that you're thinking about?
I must admit, like, this work was mainly written I can tell you the story, like, how does work like this come up? We have this yearly seminar, and Anton Kolbinger came up and said, that's a nice paper, but I don't understand. So first approach we had is prove this paper with what Jochen Geiger did. Okay, you can guess now the bias we see is different, so this is not working out. Then third, 3 weeks after we obtained the proof, Anton came and said, yeah, but I have written this paper 20 years ago. Why is this different? I don't understand. Is my paper wrong? So we did the third model with the same method, and at the moment there's no extension plan, but as soon as you have any sampling theme for any branching process, in my opinion, you can always use a method like this. The only question is, are there like interesting sampling themes that are different from those three? As far as I know, David Cheek and Jasper, they have something in mind at the moment for a slightly different kind of trees, but let's say whenever you have a sampling theme, try out a simple method like this with such uniform markers. You have just to find the right rule to evaluate them, maximum, lexicographic order, whatever, and you might be able to get the bias out, and I hope biologists or someone uses it at the end of the day. It will be hopefully published in the Journal of Mathematical Biology, so.
Okay. All right, thank you.
Thanks.
Wonderful talk. Bye.